Welcome to our third installment of Lecture 2. We're going to start off with the method of false position. And the application of the method of false position was to solve problems that can be modeled by linear equations of the form x plus b over a times x equals c. And I was rather careful to say that the application was to solve problems that can be modeled by linear equations of the form x plus b over a times x equals c, rather than saying that the application was to solve linear equations of the form x plus b over ax equals c. The fact of the matter is, ancients had no concept whatsoever of an equation. So the idea of an equation and the idea of adding equal things to both sides of an equation, dividing both sides of an equation by the same non-zero number and so forth was completely foreign. So the application is to solve problems that can be modeled by an equation of this form. And here's the procedure. First, prime the pump by making a guess as to the value of x, the solution. And we can guess any value, but the insightful guess would be a value of x that eliminates the fractions from the equation. So the insightful guess would be x equals a. Plugging in the value x equal a into the left side of the equation, we have this, which simplifies to a plus b. Well, wait a minute now. We have a plus b over a times a is equal to a plus b, but look at the original equation. The right side is supposed to be equal to c. So the question is, how can we make the right side of the equation equal to c? And the answer is brute force. Multiply both sides of this equation by c over a plus b. In other words, we divide both sides by the quantity a plus b so that the right side is 1. Then we multiply both sides by c. So multiply both sides by c over a plus b, which we do, and bingo. If we multiply this out, c over a plus b plus a, c over a plus b times a plus b, those guys cancel, we get c. Beautiful. Okay. Now let's just recap what we've done so far. The first thing that we do to solve the equation or to find the solution is to prime the pump by making a guess at the value of x. And the insightful value of our guess is x equal a, that value which will eliminate the fractions. And when we plug in a for x, this is what we get. So step 2, to get the right-hand side of the equation equal to c, we multiply both sides of the equation by c over a plus b. And we end up with this. The final step, and this is fairly important although it's a simple thing, rewrite the equation to make it fit the exact form of the original equation, which was x plus b over ax equals c. So we take this equation, make it fit the form of the original equation exactly, so that it's in the form of x plus b over a times x equals c. And guess what? To find the solution, we just look in our equation where the x's should be, We have x equals CA over A plus B. Same thing here, x equals C times A over A plus B, so that's our solution. The solution is x equals C times A over A plus B. Now, let's do an example. Solve the equation x plus 4 over 3x equals 21 by false position. The first step is prime the pump by making a guess at the value of x. And the insightful guess is going to be a value of x that eliminates fractions from the equation. So guess what? We're going to guess x equals 3. And we plug in x equal 3. And what do we get? 3 plus 4 is 7. Okay. Well, that's where we're at right now. The only problem is the right-hand side should be equal to 21. So, what do we have to multiply 7 by to get 21? And the answer is 3. Multiply both sides by 3. We multiply both sides by 3 in order to make the right-hand side equal 21. Beautiful. In the final step, rewrite in the original form and that original form was x plus 4/3 x equals 21. Okay, so we've got to take this mess and make it fit this form. So I'm just going to distribute the 3 to each of these terms in the parentheses so that the equation has the original form. 3 times 3 is 9. And 3 times 4/3 times 3, you know what? To make the equation fit the original form, I'll leave this 4/3 unaltered. And I'll distribute this 3 to what's in the parentheses. Okay, now that fits the original form. X plus 4/3 x equals 21. Well, what is x equal to? Since we have our equation written in the original form, clearly x equals 9. Cool. Now let's try this with another example. That one went well. Let's just do another one. Solve the equation x plus 3/7 x equals 15 by false position. step 1, guess, and I'll put guess in quotes, guess the value of x, because this is really an educated guess. We're going to guess a value of x that will eliminate the fractions. X equals 7 is the obvious choice here. And then we plug in. 7 plus 3/7 x equals, well, what does it equal? 7 plus 3 is 10. Okay. Well, the right side of the equation is 10. It's supposed to be 15. So that brings us to the second step. Multiply both sides. Well, let's say, what do we have to multiply 10 by to get 15? Well, we divide by 10. That'll give us 1, and then multiply by 15, that'll give us 15. So 15 over 10, or 3/2, multiply both sides by 15/10 or 3/2 to make the right-hand side equal to 15. Okay, so 3/2 times 7 plus 3/7 times 7 equals 3/2 times 10, which is 15. Cool. And then finally, rewrite the equation in the original form. X plus 3/7 x equals 15. Okay. I'm going to distribute the 3/2 to each term inside the parentheses. So 3/2 times 7 is 21/2. And you know what? This 3/7 here, I'm going to leave it as is, because I want my equation to fit the form x plus 3/7 x equals 15. So I'll take this 3/2 and I'll distribute it to this term, but I won't multiply it by the 3/7. I'll multiply it by 7. 3/2 plus 3/7 times 7. 3/2 times 7 is 21/2. And that equals 15. And it fits the original form, x plus 3/7 x equals 15. So what is x? What is the solution x? Since we have the equation written in the original form, and here's the original form, the first term has to be x, 21/2. Also, the cofactor of 3/7 has to be x. X is 21/2 in both cases. So clearly the solution, x equal 21/2. Now let's look at one more false position exercise. And we wouldn't normally think of this as being false position because we don't really have any fractions, but really any whole number is a fraction. So first thing, guess the solution. And the insightful thing to do is guess a value of x that eliminates the fractions. Well, there are no fractions here, so we could pretty much guess x to be anything. So let's take the easy way out. Let's just say x equals 1. Can't get much simpler than this. And what do we get if we do this? We get 1 plus 8 times 1 is 9. Okay. But we want the right-hand side to be equal to 33. So multiply both sides by, what? To make the right-hand side equal 33. Well, the right-hand side is 9. If I multiply the right-hand side by 1/3, that gives me 3, and then multiply by 11, I get 33. Okay. So essentially, I'll tell you what. Divide both sides by 9. That'll make this a 1, and then multiply by 33. So 33 over 9, but that's 11/3. Okay. So multiply both sides by 11/3. And 11/3 times 9 is 99 over 3, which is 33. Perfect. Okay, so the right-hand side is 33, just what we wanted. And now the third step. Rewrite the equation in the original form. X plus 8x equals 33. So I'll distribute the 11/3 inside the parentheses. 11/3 times 1 is 11/3. And I'll distribute the 11/3 to this term, but when I do, I'll leave the coefficient as 8 because the original form of the equation is x plus 8 times x. So 11/3 times 8 times 1 is 8 times 11/3 equals 33. And what is x? Well, look at the form that we have the equation in. It's in the form x plus 8x is 33. So this suggests that x is 11/3. Yep, x is 11/3. And that's our solution. Now we're going to go on to method of double false position. And the application of the method of double false position to solve problems that can be modeled by linear equations of the form ax plus b equals 0. And again, I'm not going to say that double position was used or double false position was used to solve equations of the form ax plus b equals 0, because again, they didn't have the concept of an equation. I will also preface what I'm about to go over by saying that this method, in my opinion, is completely serendipitous. So don't bother yourselves by thinking, well, why did they do that? And, how did they know to do this after that? This appears to be something this appears to be a result that is completely and totally serendipitous. So here's our procedure. Make two arbitrary guesses as to the value of x and call them g1 and g2. Let f1 be our equation evaluated at x equal g1, and let f2 be our equation, or the left side of the equation, evaluated at g2. So f1 ax or ag1 plus b, and f2 ax or ag2 plus b. And we take the second equation and subtract it from the first, and the b's wipe each other out. And we have a common factor of a here, so a times g1 minus g2. And over here, f1 minus f2. We'll keep this equation 1 in mind for future reference. Now let's go on to our next step. Recall that f1 is ag1 plus b and f2 is ag2 plus b, where g1 and g2 are our somewhat arbitrary guesses as to the solution of the equation. Well, here's what we do. Take this equation, multiply it by g2, and that yields this thing. Take the second equation, f2, multiply both sides by g1. And we take the second again and subtract it from the first, and that yields this mess. Well, the nice thing is these two terms are equal, so when we subtract, they zap each other. These two terms have a common factor of b, so we have b times g2 minus g1. And f1 g2 minus f2 g1, we'll call that equation 2. And for reference, we're going to record equation 1 and equation 2. This is what they were. Now, why are we going to record, or why do record equation 1 and equation 2? Well, here's why. We're going to divide equation 2 by equation 1. So let's see, equation 2, bg2 minus g1, there it is. And, whoops, f1, that should be f1 g2 minus f2 g1, f1 g2 minus f2 g1. So we have equation 2 on the top, divided by equation 1, ag1 minus g2, ag1 minus g2, f1 minus f2, f1 minus f2. We just divided equation 2 by equation 1. And, oh my goodness, what happens here? This factor on the bottom is the negative of that factor on top. So we can divide both top and bottom by g1 minus g2, and we just get a minus sign out front. Okay, so what? Well, let's step back and remember what it was that we were trying to do. Not as Egyptians who didn't know what an equation was, but as 21st century mathematicians, we're trying to solve the equation ax plus b equals 0 the way that the Egyptians would have done it if they had known what an equation